Hello students, today I would like to discuss infinite series, which is the syllabus of Karnataka University BSc portion paper 1, in which I would cover that Rabi's test, Rabi's ratio test. So what is the importance of Rabi's ratio test when it is applicable? So the Rabi-Duhamel's test, which is also named as Rabi's test, is a test for the convergence of the series AN, infinite series AN, where each term is a real or complex number. The Rabi's test was developed by Swiss mathematician Joseph Ludwig Rabi in the 1832. It states that if the modulus of an by an plus 1 limit as n approaches to infinity is 1, and if the limit as n approaches to infinity as n into modulus of an by an plus 1 minus 1 is L, then this limit is L. Then the series will be absolutely convergent if this limit L is greater than 1, and which is divergent if L is less than 1. First one can notice that this Rabi's test may be conclusive in the cases when D'Alembert's ratio test fails. Although this Rabi's test, as I told you, which was introduced in 1832, its importance and interpretation have largely been overlooked. The purpose of this session is to understand the statement and proof of Rabi's test, which illustrates its benefits and is situating it within its proper context. As most readers are probably aware, the ratio test and root test can both be viewed as an implicit comparison with the geometric p-series. That is, they tell us when a series behaves like a certain geometric series. Likewise, the version of Rabi's test that we are presenting will indicate when a series behaves like p-series, that is summation 1 by np for a particular p. In a sense, one can view Rabi's test as a type of comparison test that self-selects the appropriate p-series which to compare with this series. Now let us see the theorem, this Rabi's test, statement and proof of this. Let us see the statement of this. Let the series AN be of positive terms such that this limit n into an by an plus 1 minus 1 is L. Then this series AN will converge if this L is greater than 1, and it will diverges if L is less than 1. Now see that let us the proof of this theorem or this test. Let us take a P series as a Bn series, which is convergent if P is greater than 1 and it is divergent P is less than or equal to 1. Now let us consider this ratio of this P series Bn by Bn plus 1 is, Bn is 1 by n power P, Bn plus 1 is n plus 1 power P. By this ratio, by taking n power p as common and gets cancelled each other, this remains 1 plus 1 by n power p. By expanding this 1 plus 1 by n power p by the binomial expansion or binomial theorem is 1 plus p into 1 by n plus p into p minus 1 by 2 factorial into 1 by n square plus so on that. And now let us discuss, we have two cases here In the first case, let L is less than 1. We choose P such that we compare with the L, that L is greater than P, that P is greater than 1, which implies this P series, that summation 1 by n power P convergent by P series. As compared with the comparison test, which is the series is convergent if this an plus 1 by an, that should be less than or equal to Pn plus 1 by Pn. Now I can see the behavior of this Bn plus 1 by Bn, as we know that if an by n plus 1 is greater than or equal to Bn by Bn plus 1 is equal to, that is this series as we have expanded already. Then we take this one in the left hand side, that is what we are having there, and then we have arrived at if an by n plus 1 minus 1 equal to P into 1 by n, and then it is increasing the terms of n in the denominator, its power. And if I take multiply n on both sides, then this n into, if n into an by n plus 1 minus 1 greater than or equal to P remains here, and 1 n has gone here, and so on. And again, if I approach the limit as n approaches to infinity on right hand side, in the right hand side as well as left hand side, in the after first term onwards, so that all the terms which contains 1 by n terms, so that those terms which will vanishes as n approaches to infinity, so that only the term P remains because P is real. So that P, when we compare with this limit with this P which is greater than or equal to P, as I told you that if L is greater than or equal to P, which is true, that is summation, that the infinite series an converges if L is greater than 1. And in the second case, we discussed that let L is less than 1. When we choose P such that L is less than P, less than 1, means what? P is less than 1. So that implies that P series Bn is divergent by P series. When we compare with this P series with this ratio an plus 1 by an, that is an plus 1 by an is greater than or equal to Bn plus 1 by Bn. In earlier case it is less than or equal to, in this case it is greater than or equal to this P series ratio. Then when we compare with the Bn plus 1 by Bn with this series, so that now I would like to see the behavior of this P series, that is expansion of as done in the previous before case 1, so that we took it here. So then we have this an plus 1 by an, it is if this form, and when I take this minus plus 1 in this side, it becomes a minus if this in this form, and remaining the term should be in this form. When we multiply n on both sides, only P remains in the first term on the right hand side, and rest of that terms are n terms gets cancelled each other of its powers after first terms. That when we approach the limit as n approaches to infinity, and then it becomes only, that is the only first term remains P only. After first terms, this terms has been ignored because this becomes 0, since all the terms after first terms which contains the 1 by n terms and power of n terms. That's why which becomes a 0, only P. When we compare with this here, this becomes a L there. So that L, if L is less than or equal to P, which is true, that is summation an series diverges if L is less than 1. This is the proof of Rabi's ratio test. After learning this session, the students will be able to understand the history of Rabi's and when this applicable this test, and when this applicable only the D'Alembert ratio test fails that. And then we have understand that students also understand the statement and proof of the test, that so that as we have learned these, and this is the bibliography of the references as we have referred in this lecture. Thank you.